Assalamualaikum, greetings everyone. We are code 14 from session 3 of BEG 30403 Electronic Circuit Analysis and Design. We are here to present about our assignment report, which is about follow the bandpass active filter using OM. Our lecturer is Prof. Madia Siti Hawa binti Ruslan. There are 3 members in this group, which is me, Intana Jaha binti Haidat Tajuddin, Hani Farhana binti Hasbullah, and Nur Ifana Jiha binti Abdullah. So now we'll move into the introduction of the assignment. A simple active bandpass filter may be built by cascading together a single active low-pass filter and a single active high-pass filter. During the filtering process, the OM is used to attenuate the selected frequency and boost signals. There are 2 cut-off frequencies of the bandpass filter. The first one is high-pass filter, and another one is low-pass filter. So what is actually high-pass filter? High-pass filter is produced the first cut-off frequency. It is determined the band lower frequency limit, or also known as the lower cut-off frequency. A low-pass filter provides the second cut-off frequency. It will determine a band's higher frequency limit, also known as higher cut-off frequency. The low-pass filter cut-off frequency is higher than the higher-pass filter cut-off frequency, and the difference between the frequency is negative dB points determines the bandpass filter bandwidth. There are also center frequency, also known as the peak frequency response curve. In this assignment, we are required to design and simulate a fourth-order bandpass active filter using an observational amplifier OM. The specification of active filter of our group are: the mid-gain is 32 dB, the low cutoff FL is 700 Hz, and the high cutoff is 45 kHz. With the OM being selected as the amplification, 2 high-pass filter and 2 low-pass filter together with the OM are connected to perform the fourth-order band filter. As the filter order is determined by the number of RC pairs in the filter, there are a total of 4 poles bandpass filter created in this project. Our group have decided to use Multisim software in order to get the simulation. The difference between the simulation and the manual computations will be covered in the assignment. Now we'll move into the next part, which is the importance of active filters in electronic system. There are a total of 4 types of common active filters, including Butterworth active filter, Cybersurf active filter, Bessel active filter, and elliptical active filter. Butterworth active filters is able to generate a flat response in the passband and ample throughout, which can properly approximate the perfect filter fit for the system. With its slightly nonlinear phase response and sensible runoff, it can make the filter easy to understand. It will be excellent in the audio processing application. Next is Cybersurf active filter. For Cybersurf active filter, it will display a sharper cutoff in the passband together with a large phase shift close to the cutoff frequency. However, it is not usually applied to the other system and was given a rippled passband and has a very steep roll-off. This is where they ripple. The third one, we have Bessel active filter. Bessel active filter can give output with the ideal phase characteristics and usually used for pulse application, as it involves when the phase characteristic is very important in system. The last one, we have elliptical active filter. Elliptical active filter contains ripples in the passband and has several roles in conversion region of the filter. It is usually used to focus more on a particular frequency in a stopband, where it decreases the attenuation of latter frequency in the stopband. Active filter is a data acquisition system where the noise generated from the input switches from the high-speed logic will be removed using the low-pass active filters. Although there may be some cases caused by the limited sampling, which only shows few discrete levels of reduction, the filter can still reconstruct the input signal accurately before generating the output result. Apart from that, by using numerous active filters, it can work as the equalizer in electronic music. From here, you can see that there are a lot of benefits by using the active filters, and it can be applied in many applications in the world. Although it can be denied there are some disadvantages by using it, such as limited frequency range, it is still popular among the industry with its economical prices. Nowadays, the engineers are trying to create the active filter with high capacities to increase its performance. As we move forward, better quality of active filter can be found. That's all from me. I'll pass it to the next member to continue our presentation. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and hi, my name is Hani Farhana binti Hasbullah, number matric A E190129, and I will present for the calculation. So the specification of the active filter for our group are given as mid-gain A equals to 32 decibels, low cut-off frequency equals to 700 Hz, high cut-off frequency equals to 45 kHz. So from here, we can get the center frequency C, which is by using this formula. So we got 5612.489 Hz. Bandwidth, by using this formula, we got 44.3 kilohertz. The quality factor, Q, we got 0.12669. So next, the high pass filter that have three nodes were labeled with X1, Y1, and Z1. So in X1 node, we have this formula and we can get the amplifier's gain AV node. So for Y1 node, this is the formula that we use. Then we substitute J omega equals to S. So from this formula, we substitute J omega into S, which we got this formula. Then for Z1 node, we got this formula. So from here, we let R1 equals to R2 equals to R5 equals to R6 equals to R. And we let C1, C2, C3, and C4 equals to C. Therefore, the overall gain will be like this. Next, for high cutoff frequency, we know that the formula is FH equals to 1 over 2 pi RC. So we assume the value for R is equals to 10 kilo ohm. So therefore, C will be equals to 0.3537 nanofarad. So hence, we know that R1 equals to R2 equals to R5 equals to R6 is equals to 10 kilo ohm. And C1, C2, C3, and C4 will be equals to 0.3537 nanofarad. Next, if you can see here, here is the Butterworth polynomials table that we use to find the ratio for RF over RA. So here is the table. You can see in the table, we use this one because our n is equals to 4. Based on our circuit, we use fourth order band pass circuit. Therefore, in Butterworth polynomials, we use n equals to 4. Therefore, for first section of resistor ratio is here. This is the formula. Thus, R3 over R4 is equals to 0.152. Then we assume that R4 is equals to R, as we know R equals to 10K. We substitute the R4 equals to R, which is 10K. Then we bring it up and we got 1520 ohm for R3. For the second section of resistor ratio, which is R7 over R8, we got 1.235. Therefore, we assume that R8 equals to 5K and R7 will be equals to 5K times with here the ratio, which is we got 6.75 ohm. After we done the high pass filter calculation, we have to calculate the low pass filter. So the low pass filter calculation for the third partial filter, which is the lower band pass filter, there have three nodes were labeled with X3, Y3, and Z3. So at X node, this is the formula. For amplifier's gain, this is the formula. At Y3 node, this is the formula. At Z3 node, here is the formula. Then next, we let the R9 equals to R10, R13, and R14 equals to R. And C5, C6, C7, C8 will be equals to C. So this is the overall gain will be, which is the formula. The formula of high cutoff frequency is here. Thus, we have assumed a new value of R equals to 7 kilo ohm. So C will be equals to 0.5025 nanofarad. So R9, R10, R13, and R14 will be equals to 7 kilo ohm, and C5, C6, C7, C8 will be equals to 0.50525 nanofarad. For the calculation of R11, 12, 15, and 16, it will be using by the Butterworth polynomials table to determine it. So we use the n equals to 4. So we use n equals to 4 in the Butterworth polynomials table. And for the first section of resistor ratio, we got R11 over R12 equals to 0.152, and for R12 we assume that it is equals to R, which is 10 kilo ohm. We get the R11 is equals to 1520 ohm. For the second section of resistor ratio, this is the formula, and we got R15 over R16 will be equals to 1.235, and R16 we assume it as 20 kilo ohm, and R15 will be 24700 ohm. That's all from me for now. I'll pass to my next members for the next explanation.
Next, I know Ifanaji how to explain the circuit simulation of this project. So basically, we are using multism to create and analyze the circuit. So as you can see from the simulation, we are using 18 resistors with different values, and also there are 8 capacitors that we use with two different values, which are 0.3537 nanofarad and 0.50525 nanofarad. There are 5 operational amplifier that we use in this simulation. So at the upper part of this simulation, it is the high pass filter, and the below part is lower pass filter. So we can note that this simulation is the FOD or the bandpass active filter. So to analyze this circuit, we using the board plotter and the function generator to get the graph. So when we run the circuit simulation, we get the graph is like this. It is the frequency versus gain graph. From this graph, we can know that we get the low cut-off frequency and the high cut-off frequency from this graph. From the graph, we can get a comparison between the simulation and calculation. So for low cut-off frequency, for calculation, we get the value 700 Hz, but from the simulation, we get 731.92 Hz. For center frequency, from the manual calculation, we get 5612.49 Hz, while for simulation, we get 5216.17 Hz. For the high cut-off frequency, the manual calculation, we get 45,000 Hz, but from the simulation, we get 37174 Hz. The manual calculation for the bandwidth, we get 44,300 Hz, while for the simulation, we get 36,442.08 Hz. For analysis and discussion, in this part, we will analyze the result that we got from the simulation of the FOD or the low pass filter that we have simulated in Multism software. From the circuit that we have designed, we were able to apply the specific parameters that have been assigned to our group. Based on the simulation result, the low cut-off frequency is slightly different with the specification that had been provided by lecturer, which is the given value is 700 Hz, while the value that we got in the simulation is 731.92 Hz. The difference between the simulated value and the theory value is 31.92 Hz. In the meantime, the value for high cut-off frequency also has a big difference, which is the assigned value is 45 kHz, and the simulated value is 37.174 kHz. The difference between both values is 7.828 kHz. However, for center frequency in the theory calculation is 5612.49 Hz. In the simulation result, we got 5216.17 Hz, which differs by 396.32 Hz from the calculation. Last but not least, it has been proved that each value got slightly different between the simulated value and the theory value. Even we did not get the same value as in theory, but we managed to simulate the circuit that we have designed. That's all from me. I will pass to the next member.
Now I will explain for the conclusion. So in conclusion, we have simulate and design a fourth order band pass filter using op-amp. Our group, which is group 14, got the specification of the active filter from our lecturer that consists of mid gain, which is 32 decibels, low cut-off frequency is 700 Hz, and high cut-off frequency is 45 kHz. So in this assignment, to simulate the program, we are using Multisim software to design the active bandpass filter. So the circuit that we designed for this bandpass filter is using the op-amp. It is formed by cascading two high-pass filter and two low-pass filters together with the op-amp. So at the end of the circuit, we'll have the non-inverting amplifier.
With this, it marks as the end of our presentation. Thank you for staying with us until the end of our presentation.